Okay. Well, there's a possibility that I might call somebody today. We'll see if the mood strikes. So, depending on how far we get. Yeah, don't. It's not time for it to freak out. So, well, freak out about something else. Okay.
My dog has been in the house since 7:30 this morning.
Oh.
I teach at 8. I'm here all day from 8 o'clock to 6:30 at night.
Oh. Alright, so we started talking about differentiation last time. So, quick recap. We're approximating the derivative of a given function f at a certain point x naught by the derivative of an interpolating polynomial evaluated at x naught, which would just be a combination of the values of f at selected points, and then we'd be differentiating the accompanying Lagrange polynomials at x naught. Okay. So what I'd like to do today is, sorry, one last item to recap. The error would just come straight from the error formula for polynomial interpolation, which would be n plus first derivative at some unknown point. Was that someone else's device? Okay, good. I didn't want it to be my computer freaking out like, hey, I'm gonna stop recording or something. Okay. You set off Siri?
Yeah, you can turn that off now.
Oh, okay. Yeah, because I've been setting it off accidentally a few times. Okay. And then we have a product going from 1 to n of x naught minus xi. Okay. Now, so the thing is, if we just determine which points are we going to use to approximate a derivative at x naught, then we can develop some specific numerical differentiation rules. So,
Dr. Lemers,
yeah.
in the error, the p sub n prime of x, is that an x naught as well? The second term of the error?
Oh, that?
No, in the
Oh,
error.
yeah, that should be.
Okay.
Yeah.
So how about I? Shouldn't it be xj, x naught minus xj?
Oh, should be.
Or that, yeah.
Okay. Yeah. All right. Was that all the mistakes? Just making sure. There weren't more. I actually have a theory that once a piece of mathematical writing or code gets large enough, it can actually contain infinitely many mistakes. Or at least things that could be improved. All right. Now, so which points should we use? So what you could do is, so usually, not always, but let's go for this case, we have some sort of equal spacing. So we want derivative at x naught, And so we use the value of f at x0, but also neighboring points, x0 plus h, x0 plus 2h, and so forth. It also points to the left. Okay. And certainly how many points we use, which points will affect the coefficients and the accuracy and all that. Okay. Now, I'm going to give a few of the best known differentiation rules along with our error formulas that certainly could be derived using this, but then I'll pick out a more interesting one to actually go through the derivation using these Lagrange polynomials. Okay. So these come up often in numerical methods for ODEs and PDEs, for instance. Okay, so forward difference. And write down n equals 1 because we're only going to use 2 points. We're fitting f by a linear function. So f prime at x0 is equal to f of x0 plus h minus f of x0 over h. Where have you seen this before?
So,
Definition of a derivative. Yeah. Now, it's not exactly equal to, but I'm writing equal because I have more to write to include the error. So the error term for a forward difference is minus f double prime at an unknown point over 2 times h. So this is your error. And what you have is an expression that's proportional to h to the first power. So we say the error is big O of h. In other words, it is first order accurate. Okay. All right. So that uses only these 2 points. It doesn't use any data to the left of x0. But certainly you could. For instance, actually, what if you just replaced h by minus h throughout? It's really annoying how this board is rattling. Okay. So that also, we're using a linear approximation. And yeah, really, you can just swap h and minus h. x0 minus h over h plus so that also is first order accurate. So you look at the power of h in the error to determine what order of accuracy is it first order, second order, and so on. And then we have one more that's very well known, center difference. So there we bump up n to n equal 2. We fit f by a quadratic function. So interpolating 3 points, x0, x0 plus h, and x0 minus h. You can think of it as the average of these 2. So that'd be f of x0 plus h minus f of x0 minus h all over 2h. And then the error is, so what happens is, because we're averaging these 2 approximations, it's like these 2 errors basically cancel each other out, which is quite nice. And so the error in this case is f triple prime at an unknown point over 6 times h squared. So because h is squared, we say the error, this center difference is second order accurate. Now, it might seem strange that here I've increased the degree of the approximation. So instead of using a linear polynomial in these cases, like in these cases, we're using a quadratic one. But we only have two values, f of x naught plus h, f of x naught minus h. The reason is we're actually fitting f at 3 points, x naught plus h, x naught minus h, and x naught. It's just that the coefficient of f of x naught in this formula happened to turn out to be 0. So, because these coefficients, or these weights, are what we use to linearly combine the function values, and it could happen that a certain weight is 0. But it still played a role in the interpolate. All right. Now, so I want to give a rather frivolous example, admittedly, as to why numerical differentiation rules like these are nice when we already have all these symbolic differentiation rules, like the ones you learn in Calculus 1, that could be used to differentiate such a wide variety of functions. It's not like integrals where there are certain integrals you just can't do. If you have any combination of polynomial, rational, algebraic, trigonometric, exponential, logarithmic functions, however they're combined, you can differentiate them, and you can have software differentiate them. But in a lot of practical applications, if you want a derivative at a certain point, you only need a certain amount of accuracy. You may not need it to be exact. So if you compare the work involved, especially if it has to be done by computer, I think this example can help get the point across. Okay. Now, this function I'm going to use as an example may not be one that would occur in nature, like a typical application, but you never know. Okay. But I wanted to come up with a function that has a rather monstrous derivative. Okay. So sine squared of and I just made this up. Suppose I want the derivative at a certain point, let's say 0.25. Option 1, we go ahead and compute a derivative using all the rules you learned in Calculus 1. That's a nice, simple expression, because you're having to apply the quotient rule. So, oh God. But I am going to write this out. I'm in all the way on this. This right here is just the derivative of the numerator. And let's not forget the good old chain rule. And I actually carried this out a long time ago, probably about 10 years ago. Probably wouldn't have the patience to do it now. Okay, that's the first half of it. And the thing is, there's many software packages that perform symbolic differentiation. That's pretty expensive for a computer to do because it's all about maintaining data structures for. If you think of each function as an expression tree, like involving arithmetic operations, application of functions like sine and cosine, and so forth. And if you have like an expression tree representing a function, you can write code that would generate a new expression tree representing a derivative. As you can see, the expression tree for this function is kind of mushrooming compared to that one. Almost done. And yeah, evaluating the function itself is no picnic. But if you have an exact representation of derivative, that can, as we see in this example, be a whole lot more troublesome to evaluate. Okay. So then you can set x equal to 0.25 and get the answer. And what we get is the several decimal places, minus 9.0666, 98770. Okay. But this is not really playing to a computer's strengths in terms of having to move expressions around, move a lot of data around to try to keep track of what the structure of this function is, and then actually carry out the evaluation. So option 2 involves only working with f itself, which in this case is a whole lot simpler. So we can use center difference and h equals 0.005. So f prime would be f of 0.25 plus h, so that's 0.0255, minus f of 0.25 minus h, so that'd be 0.0245, all over 0.01, because that's 2h. So a whole lot less work done computationally, but what do we get for an answer? So minus 9.067, etc. So of course it's only an approximation, but the error is 0.00077. So, and the thing is, if we had reduced h, like if we chose a smaller h, then up to a point we can get much smaller error for exactly the same amount of work. So if all we want is approximation, because in a lot of applications you only expect so much accuracy anyway. You have all these sources of error to deal with. So trying to get an exact value for one small part of your computation when there's a lot of error everywhere else is a waste of time. So, so really, I call this a frivolous example, but doing this to get this exact in the context of real application also would be considered frivolous, really. So, because computers were designed to perform arithmetic as quickly as possible, and so numerical methods do a better job than analytical methods of taking advantage of that strength. Okay. Now, so now what I'm going to do is step through an example of deriving another differentiation formula. So not one of these. Okay. Because this one is more accurate. But suppose I want a formula for computing a derivative at a second order accurate, like this one, but it only uses data on one side of x naught. Because this requires f of x naught plus h, f of x naught minus h. What if you don't have data available on both sides? What if you're on an endpoint of your domain? So maybe you can evaluate f at points to the right of x naught and not the left. Sometimes that happens, like for boundary value problems for differential equations. So, so sometimes one-sided differentiation rules like these are quite valuable, whereas this is a two-sided rule. Okay. So I'll go ahead and derive a rule that uses x naught plus h, and x naught minus h using these Lagrange polynomials. And we'll also get the error. Okay. So one f prime of x naught using x naught plus h, x naught plus 2h. All right. So for this, I need Lagrange polynomials for these 3 points. And we've seen before how to construct Lagrange polynomials, so we're going to go through that process. It's just that once we have them, then we need to differentiate them and compute the derivatives at x naught. Okay. Now, so I have 3 polynomials altogether. So our interpola is going to have degree 2, so it's going to be 1 less. So our first one is going to be equal to 1 at x naught. And it's equal to 0 at x naught plus h and x naught plus 2h. So does anyone remember from last time how we go about constructing a polynomial like that?
We would do x minus x naught plus h times x minus x naught plus 2h
Yeah, and
over x naught minus x naught plus h, and then x naught minus x naught plus 2h, x naught.
yeah, and definitely want to be careful of your parentheses.
Is the
And
one
then would
that's
be-
not supposed to be
That,
Yeah.
yeah.
Okay. Yeah, I think I've been already thinking ahead of the denominator. Okay. Now, well, fortunately, we have these x naughts canceling out. Okay. Now, this is something I don't have worked out in the notes, but I think it'd be a good idea, if possible, to make this simpler. Okay, I'm going to introduce a shorthand here. A variable s equal x minus x naught. Let's see. Actually, x minus x naught over h. Because what that would do is that's going to map these points, x naught, x plus 2h, x naught plus h, x naught plus 2h, to points s equal, well actually, what would the s values be corresponding to these? If I plug in each of these guys for x, what would I get for s?
You get 0 for the first one.
Yep.
Are you gonna get 0? You're gonna get 0,
You
1.
get 1 for the second
Yeah, 0, 1, and 2.
And 2.
So instead of writing out Lagrange polynomials for x naught plus h, x naught plus 2, maybe we get away with 0, 1, and 2, and that'd be a whole lot easier. So if I replace these with, write them in terms of s, then I'm going to get, h times, okay, so this is, well, I'll do this one step at a time. Because that's the same thing as saying x is equal to
Excuse me.
x naught plus, yeah, okay. All right, so if I go ahead and fill that in, then I have, okay, the x naught cancel out, so I get h times s minus 1, and then if I fill that in here, I get the x naughts cancel again, and I get h times s minus 2, and then down below I have minus h and minus 2h. All the h's are going to cancel. Okay. So that worked out quite nicely, that I could just do my interpolation at 0, 1, and 2 rather than x naught plus h and x naught plus 2h. And we're going to do something similar when we get to differential equations, talking about multi-step methods, where we can again simplify. Because if I do these Lagrange polynomials in S, I can get the ones in X just by undoing this transformation. Okay. Now, so now I want this next polynomial to be 1 when S is equal to 1, and then 0 when S is equal to 0 or 2. So we just do all this in terms of S, and that'd be a whole lot easier than what we get. Yeah. Okay. Yeah, so minus S times S minus 2. Okay. And then finally, the last one is equal to 1 when S is equal to 2, and 0 when S is equal to 0 or 1. So what would that be?
S times S minus 1 over
2.
Yeah. So it's 2 minus 0 and then 2 minus 1. Right. So S times S minus 1 over 2. Okay. Now, you all right?
Yeah, I'm just gonna pick up.
Okay. Now, for Lagrange polynomials, what we would do if we written everything in terms of x, we would then differentiate those and plug in x naught. But if we want to stick these simpler polynomials in S, we would differentiate and plug in what? Okay. If we stuck with x, like this kind of Lagrange polynomial in this form, we would then differentiate, going back to the formula I did at the beginning of class, we differentiate the Lagrange polynomials to get the weights and plug in x naught. But if we want to stick with polynomials in terms of s, what would the equivalent be? If we could differentiate these, then what would we plug in for s? So,
X minus X naught of X.
well,
Did you plug in, was it 0?
0, yes, it is 0.
X equals X naught plus HS, to get X naught, it would be 0.
Yeah, so the derivative with respect to x of Lagrange polynomials as a function of x, evaluated at x equal x naught, that's what we really want. So these are our weights. So we have to end up with those. But anyways, instead we differentiate with respect to s, these Lagrange polynomials that are now a function of s, and we plug in 0. Now, but can anyone tell me what I've forgotten? There's one mistake here. Because differentiation with respect to x is not exactly the same as differentiation with respect to s. How do I correct it? It is 1 over h, and how did you get that?
Differentiate X. You get dx, so then you
I need, ds dx, because ultimately it's differentiate with respect to x. And we have a formula right here, we just differentiate. So s prime is equal to differentiate this. So we get 1 over h. Chain rule is what we needed to use there. All right, so we can take these polynomials, differentiate them, plug in s equals 0, and then we throw in a factor of 1 over h, and then we have our coefficients. Okay. So questions about that before we actually go ahead and carry it out? Okay. All right. Now, okay, I want to write these in simplified form. So that would be s squared minus 3s plus 2 over 2. The next one is minus s squared plus 2s. And then the last one is s squared minus s over 2. Okay, so all right, what are derivatives?
The first one is 2x minus 3 over 2.
Then
And the second one is negative 2x plus 2.
Yeah.
And then the last one is 2x minus 1 over 2.
All right, and then we just plug in s equals 0. So, all right. So what are our weights? So for f of x naught, f of x naught plus h, that's equal to 1, and f of x naught plus 2h. Okay. So we just plug in
You
s.
just negative 2, 2 and negative 1/2. But then what about the 1 over h that you have to multiply?
Yeah, we have to throw that in there too. Yeah.
So
So,
negative 3 over 2h. 2 over h.
yeah, and it's 2 over h. I'm going to write it as 4 over 2h to have a common denominator, but yeah. Okay, so that's how we combine all the function values. So now I can go ahead and write out the actual differentiation rule. sure I have it on the site. Okay. Oh, yes, I do. It's under the September 14th entry when I was supposed to cover this. Oh, except now it's going to try to fire up MATLAB to open it. Dang it. Okay, but I actually make this change a variable to work with just interpolating at the integers to construct a differentiation rule. Okay. Now, okay, so to write out what the final rule is, we just take those function values that we're using, f of x naught plus h, and plus 2h, and multiply them by those weights and add them all up. So f prime x naught is equal to, so we have minus 3 f of x naught plus 4 f of x naught plus h minus f of x naught plus 2h all over 2h plus error, which we're going to figure out in a little bit. Oh, wow, typo in the notes. So looking at the rule that I have here, it's like there's no minus sign, but there's supposed to be. Okay. I remember to fix that in the textbook. Okay. Now, okay, so any questions about how the rule was obtained? All right, so you make a Lagrange polynomials, differentiate them, plug in x naught, or you make a change of variable to make it easier. Now, one thing I want to point out before we do the error term is you'll notice that the coefficients, so minus 3, 4, and minus 1. Okay, I'm going to write down coefficients for other rules we've seen too. And these are all points that we've ever used. So for a forward difference, we have f of x naught plus h minus f of x naught. For a backward difference, we have f of x naught minus f of x naught minus h. For a center difference, we have f of x naught, well, we have over 2h in the denominator, so these are our coefficients in these cases. And all of these have a factor of 1 over h, I'm just not writing that. And then a 3-point forward difference, which is basically what we have here, because it only uses points to the right of x naught. The coefficients in that case were minus 1/2, 4/2, and then minus 3/2. Now, all different coefficient patterns, but can anyone see what they have in common? What property all 4 of these sets of coefficients have?
Less are negative, less are positive.
On the right track.
Alternate?
Um,
Well, there's only two, so.
yeah. But they alternate here as
Differences
well.
are 1.
What?
A unit, the difference, oh, of course it should be, sorry.
Difference is zero.
Yeah, but or
There's
the,
negative three minus one.
yeah, but the sum of all the coefficients is always 0. Okay. That's going to be true of any differentiation rule of this kind that's based on using polynomial interpolation. And the reason is, suppose your f of x was a constant function. Then you'd have f evaluated at whatever point, always being a constant. You could factor out the constant, and what's left? The sum of the coefficients. But the derivative of a constant function is 0. So to make sure that at least get that simplest case correct, it's always going to work out that way. Okay. Now, how do we get the error? We have a formula for that. So the error, we have n equal 2, because we use 3 points. So it's f triple prime at an unknown point over 3 factorial. And then we're going to have x naught minus x naught plus h. So I'm just using the formula that I gave some time back. We're just subtracting x naught from each of the other points. So we get f triple prime over 6, and then we get minus h minus 2h. So we get minus f triple prime over 3 h squared. Actually, better make. Oh, wait a minute. No, it's positive. Negative, negative. Okay. All right. So it's second order accurate, which is what you'd expect from using 3 points. So that's what happens most of the time.
Why is it n equals 2 again?
Oh, because however many points you use, the degree of your interpolant is 1 less.
Like always?
Yes. Yeah.
But except.
Oh, I know. No exception in that case. I know. All right. Okay. Now, so I should mention that the same approach can be used to design differentiation rules for higher order derivatives, second derivatives and so forth. But one thing it kind of bugs me that even though using Lagrange polynomials, so like you take a Lagrange polynomial, take a second derivative and plug in x naught, that will all work. I do not honestly see how to develop an error formula in the same way, because you have to take the error formula for the interpolating polynomial and differentiate that multiple times, and that gets really messy. So I'm going to show you a different approach for getting a second derivative formula that's quite well known, and also an error formula, but it will not use Lagrange polynomials. That's because I don't see how to do that and get the error. But in this approach, an alternative approach to differentiation rules that you should be aware of anyway, even though it's not really dealt with much in a textbook. Okay.
Is that, let's see, is that, I wrote down last time, it was with respect to x. Is that still true here?
Differentiating.
That point, that, squiggly.
Oh yeah,
I'm assuming it's a z, but.
yeah, squiggly is a function of the point you're evaluating at, so it would depend on x naught.
X naught, okay.
Yeah. Okay. So for higher order derivatives, you can use Taylor series or Taylor expansions. So as an example, if I write out Taylor expansions of f of x naught plus h and f of x naught minus h, if I don't fill in f of x naught as well, I want to use all 3 values to get second derivative. So plus h, we have h f prime of x naught plus h squared over 2 f double prime plus h cubed over 6 triple prime plus h fourth over 24 quadruple prime, and so on. I won't need to go any further than that. And then similar for f of x naught minus h, where all I'm going to have to do is replace h with minus h. That's going to cause every other term to go negative. Okay. So what I'd like to do is combine these linearly in such a way as to isolate f double prime of x naught. So what I could do, for instance, is if I were to add these first ones, you would see that the first derivative terms would cancel out. But I also need to multiply, I need to choose coefficients that I can write here to make sure that any terms involving lower order derivatives, they have to cancel. So for instance, I definitely know that these coefficients should be the same in order to get these to cancel out. So I need these to go away. But they should also sum to 0. All three coefficients, so that all of the f of x naught values will go away. So I need these to equal the same thing, and then whatever these sum to, I should fill in minus 2 times that here, so that all the coefficients will be 0, or sum will be 0. So by choosing these coefficients, I'm guaranteed to cancel out, all of these. But I need the coefficient of f double prime to equal 1. So, so what should I do? I can choose A to be anything I want, and these guys will still cancel. What should I choose A to be so that when I combine these guys, I get just f double prime of x naught? 1 over h squared. Yeah, that'll do it. Okay, so f double prime at x naught is going to be equal to f of x naught plus h minus 2 f of x naught plus f of x naught minus h all over h squared. And then anything else I get is going to be error. Now, so what's happening is my error terms, I basically take all these other terms and move them to the other side. So I'm going to have a minus here. So I'm going to have, well, what happens to these terms? Those are going to cancel. All right. So now I'm going to take 1 over h squared times this plus 1 over h squared times this. So I have 1 over h squared h to the 4th over 24, fourth derivative of x naught, and then again, same term. Okay. So when I combine all of this, I'm going to get h squared over 12, fourth derivative, x naught, plus other terms. But this basically gives me my error. It shows that it's second order accurate. Okay. So at least using Taylor expansions for whatever order derivative you're computing, you can get an error formula. So really the error formula, as stated like with the other formulas, I have h minus h squared over 12, fourth derivative at an unknown point, and that would encapsulate the entire error. Okay. All right. So this second derivative formula, very popular in methods for solving ODEs and PDEs, since a lot of those of interest are second order, or involve second order derivatives. Okay. All right. So if you're using more points, you can get higher order accuracy, or you can also do higher order derivatives. And basically what you're doing is you're solving a system of linear equations. Because you're trying to get certain terms to cancel out. You're trying to get certain other terms to add up to have a coefficient of 1 for whatever derivative you want. So and that's a system of equations you just go ahead and solve. So nothing to it. Okay. Any questions about that? Okay. Well, actually, that's all I need to cover about differentiation. I feel like I'm missing something else. There's something else I can do. Okay. There is one thing that's worth pointing out about differentiation rules in general. Because what this error formula is saying is the smaller you choose h, the smaller your error will be. But in a practical setting, we're actually carrying this on a computer, that's not entirely true, because this is only about the error due to Taylor expansion. But you also have computer arithmetic to think about. Because what if I chose h to be incredibly small? Then what would happen to each of these expressions? They'd be very close to each other. So f of x naught plus h could be almost indistinguishable from f of x naught minus h. As those values get closer to, as the x values get closer together, but you're plugging them into f, you could be in a situation where you're subtracting numbers where the result is supposed to be nearly 0, but you have a lot of cancellation error. So these formulas suffer from what is called catastrophic cancellation. And that occurs whenever you have a situation where the absolute value of x minus y is much less than the absolute values of x or y individually. For example, if you're subtracting numbers like let's suppose you have 8 decimal places. So here are your 8 decimal places representing this number, and then you have 8 decimal places representing the number you're subtracting from it. So the first several digits cancel out. So you might think, oh, I have 8 decimal digits of storage, so I can have 8 decimal digits of accuracy on my computations. But as a result of this subtraction, you just gave away 6 decimal places of your 8. So this answer, because you only retained significant digits, is far less accurate than either of these. Because whatever digits that we're supposed to have here, you don't have them. So this is a big problem. And as a result of this, as h gets smaller and smaller, for a while you see your derivatives getting more and more accurate, but at some point that stops, and this arithmetic error becomes dominant and causes the error to increase. And we did this in 460, 560, where we tried this out in MATLAB, like computing derivative with smaller and smaller values of h, the error is going down, 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 and then it started going up. So you have to be careful about that. With and it's because whatever error you get up here, you're dividing by power of h, so that's going to magnify it. And if h is particularly small, it's going to get magnified a lot. So, so even if the error up here isn't all that bad, it's that magnification that kills you. Whereas with integration, since that's the opposite operation of differentiation, doesn't really suffer from these things. It's a lot more numerically stable. So that's one thing to be aware of, that don't just think you can just use as small as h as possible and you're just going to get more accuracy, because it's going to blow up in your face.
Excuse me, so what makes this plot goes up after going down?
Because you have multiple sources of error. There's error due to truncating a Taylor series expansion, and then there's error due to computer arithmetic limitations. So for larger values of h, but as h is decreasing, the Taylor series expansion error is going to 0. So that error is definitely going to 0, no matter what. But your other sources of error can, as h gets smaller, it can become larger.
So when it goes to increase, it means that part of error is not related to this one. It relates to others.
Yeah, I haven't bothered to quantify round-off error at all. It's like it would be like a separate term. So because this analysis here doesn't take round-off error into account. So what you could do, for instance, is if you assume that each of these evaluations of f has some error in it, and maybe you could come up with a bound for that error, then you could do a more detailed round-off error analysis that separates the error into two terms, like a term like this, and another term that would actually be proportional to a negative power of h for the round-off error. And you can actually try to find, you can treat it like a minimization problem, like for what value of h is the error minimized, to balance the two effects.
That was my second question. So how to find that best value for h?
You can't do it precisely, because the best you can hope for is maybe come up with a bound for this error, and that depends on the function. So any analysis you could do is really advisory at best. And the thing is, the higher order accuracy of a rule, the less you can get away with, because that h gets raised to a power. And but again, if a rule is higher order accurate, you don't need a very small h, and you still get a lot of accuracy. But yeah, it's something that you have to be careful about. Okay. Now, we have some time. I can call on somebody.
Haley.
Okay. All right. So Haley's going to do 1.8.
Can we just write it on the board? Or do you want me to
Yeah.
while I'm doing it, or what?
Well, I mean, you can treat it like you're giving a lecture.
Sorry, I'm just pulling up the problem.
Oh.
Just the terrible topic, okay, so 1.8 says, suppose that the function f has a continuous second derivative that f of squiggle equals 0, and that in the interval from x to squiggle with x is less than squiggle, I just love saying that is so fun. F prime of x is greater than 0 and f double prime of x is less than 0. Show that the Newton iteration starting from any x0 in the interval converges to squiggle. So, let's see.
Maybe you can write down the most important facts from those.
Yeah, that's what I was gonna do. Let's see, we know squiggle equals 0.
It's a nice squiggle thing.
Thank you. Just super extra squiggly. Then f prime of x is greater than 0. F double prime of x is less than 0 on the interval. I'm just going to say interval x to squiggle. Let's see where this is like a big X. X is less than squiggle. So to do this, I used the theorems 1.8 and the assumptions from the theorem 1.8 and 1.9. Do you want me to write about those or just kind of do it?
That probably takes too long, but yeah.
Yeah. So you can look them up if you want to. But let's see. Let's suppose. Squiggle minus x of k is less than some h, which h is the minimum value of either delta or 1 over a, and a is defined in I think 1.8. Let's see, where x of k is in your interval, should I? Let's see. So by Taylor's theorem, we can expand around x of k. So let's see. F squiggle is equal to f of xk, plus squiggle minus x of k, times f prime of x of k, plus this nonsense, squiggle minus x of k squared over 2 f double prime of what's this called again? Eta, that's it. Eta. I should know this. I was in Greek life. Where let's just say eta is between the values of x of k and squiggle. Okay, so basically it's in the interval as well. If it's in between, if this is in the interval and this is in the interval, it's obviously in the interval as well. So, do you mind if I go over here?
Oh, okay, so yeah, go ahead.
Okay.
I think move this.
Sorry, I write really big. Okay, so if I really kind of want to do some rearranging to this. So first, I'm going to go ahead and distribute my f prime. So f of squiggle equals, this is all equal to 0 as well. Let's see, f squiggle equals f of, how much time do I have anyways?
8 minutes.
Oh, okay. For some reason I thought I had less time.
Yeah. Go to minus.
Yeah, the XK.
Did it really? Oh, thank you. Then I kind of want to start making this look like Newton's method. So I know that Newton's method is x to the k plus 1 equals x of k minus x of k over x prime of x k. Let's see. So, what do I want to do? Let's see. Sorry, I didn't actually do this on my paper, so I'm trying to remember what exactly I need to do. So that is equal to 0, so I need, let's see, this and this on the other side. So, let's see, x, k, squiggle, x, equals x negative k. Okay, then if I, let's see, divide everything by f prime of x of k, I'll get, let's see, squiggle plus squiggle minus x of k squared over 2 times f prime of x of k times f double prime eta k is equal to, and then again some rearranging, but still, x of k minus f of x k over f prime x of k, which this is just, this is just my Newton's method. So from this, let's see, I can get, let's see, squiggle minus x of k plus 1 is equal to, pretty much just this portion. So, let me short, sorry, I write really big. Squiggle minus x of k squared all over 2 f prime x of k f double prime eta of k. Wait. Let's see. Okay. Which this implies, let's see. If I pick a random point, this is less than squiggle provided. Am I missing the negative
I'll
sign?
be able to do
Well,
that.
because we moved back to the other side, that needs to be negative again.
What needs to be negative?
The right side.
Ah, thank you. Sorry. Oh yeah, I am. Sorry, I have it on here. I just missed it. Let's see. Provided that x to n is in our interval. Okay. So, let's see. Since f is like monotonic and increasing, I was going to go back over here. Like, f's supposed to look something like, well, not at all like that, but something like this, where, like, this is our epsilon, maybe our x is over here. Since it's supposed to be concave down and our first derivative is positive, I think it's going to be looking something like that. Let's see. So, let's see. Okay, so if x sub 0 is in our interval, let's see, the sequence x sub n is also in our interval. And since it's bounded above by our squiggle, let's see, it converges, and since our squiggle is the only root, it converges to squiggle. Did I write that?
No.
Or, okay, what did I do wrong?
Is it quadratic?
Yeah, it's quadratic,
Yeah,
but I didn't think we were supposed to prove that it was quadratic. I mean, I
I
can.
don't remember, but the thing is, you're missing something else.
What did I
Yes.
miss?
Because you showed it's bounded above by a squiggle, but you did not show that the sequence is increasing, which involves showing that xn plus 1 is strictly greater than xn,
Oh.
which you can get from the assumptions that you have. Well, this is, and since this is xk plus 1,
No. I mean, isn't it given the first derivative is greater than 0?
Yeah, I mean,
well,
it's-
but the thing is that alone.
Is not.
Well, I mean, you can use that to show that xk plus 1 is greater than xk. Well, okay, so how can you use this to be sure that xk plus 1 is strictly greater than xk? Because, like you just said, the derivative is positive.
Oh, because isn't this, okay, so, wait, xk plus 1 is equal to this, so this is a positive number.
No, yeah, it is positive.
Yeah, this is positive.
What do we know about the sign of f?
Oh, this is negative, so xk plus 1 has to be larger, because this is going to be adding something onto
Yeah,
it.
and you need to include that to show that the sequence is steadily increasing.
Like that? I mean, can I literally say that though? I mean, just
Well,
like,
now you can, but the thing is, you have to use with your knowledge of the derivatives to show that, yeah, f really is negative on the interval, which your picture shows, but, yeah,
oh,
Yeah.
you have to, okay.
because if you're to the left of squiggly, if a function is increasing towards the root, then it has to be negative.
Yeah.
Yeah.
I have a question.
Yeah.
How do you get squiggle is greater than x n plus 1 from that equation?
I just said, wait, this?
Yes. Is it a conclusion that you get from that equation?
Yes, it is.
So how do you get that? Because it's equal to a minus thing.
But the second derivative is negative.
Okay, yeah.
Yeah, so from the signs of all of these pieces, this has to be positive. Okay.
This is why I should never teach on a chalkboard, ever.
Okay.
So,
Yeah, I teach trig next semester, I'm gonna cry.
Well, we're out of time anyway. Okay. Alright. Okay, so we'll start integration next time.